I'm going to have to be so good this lecture.
Excuse me, could you ask His Holiness to keep it down a little bit, please?
I wouldn't presume.
I mean, my name's Aaron.
Okay. No, okay. He knows that he can't talk. Guys, give him more credit. Okay, so we have the final lecture of the dynamic systems portion of this class. Although we have homework this week and next week that are still on system dynamics material, specifically the Rowell and Wormley text, chapter 15 problems. I reviewed them, and after this lecture today, we'll have covered all the material needed for those. And then this week, this is another short week, as is next week, but we'll be doing, today we'll actually start a little bit of control stuff. So we'll talk more about that when we get there. But this is the last topic I wanted to cover in the dynamic systems portion. So, we've kind of built up this entire frequency domain apparatus, and this is sort of the last, I guess, sort of key topic, but there's so much to it, and I could talk for the rest of the semester on frequency domain stuff. There's just a lot there. So we have all the tools needed, though, to explore the frequency domain. And in this lecture, we'll kind of discuss probably the one of the last key concepts, and it'll really set you up for your vibrations class next year. Okay, so, and then there are a couple of you who already took that class. So I don't know what to tell you. You're welcome. That's just my default thing to tell people. I don't know what to say. Okay, so we have the lecture called Periodic Input Frequency Response. So let a system H have a periodic input U represented by a Fourier series. So we've had periodic inputs before, but the one type of periodic input that we've really considered in detail is a sinusoid, right? It's just sine. Sine input, what is the output? Oh, we found out you just change the amplitude, you just change the phase, and that's how you get the output. So with the lecture today, we're going to expand the class of inputs to any periodic input. So for real numbers, A0, omega 1, which is going to be our fundamental frequency, AN and phi n, let 6.45 be the Fourier series representation of our input signal. So this is slightly different than the Fourier series representations we saw before with the trigonometric form, because we only have one sine in there instead of a sine and a cosine, right? But we do also have a phase added, so that takes care of that part. Remember how we can combine a sine and a cosine together to be one sine with a phase shift? That's what we've done in this formula. So if you have a sine with a phase shift and all the different frequencies and all the different phases associated with that, I used script A instead of regular A because this is slightly different than the formulation before. We used A in, so I don't want to confuse us. I'm all about keeping confusion to a minimum, so you're welcome. So A0, so A0 is the DC offset term, right? It shifts the whole thing up and down. And so this is our usual representation. The nth harmonic of this input, of course, is un of t equals, so we just take out one term, so I'm going to try to draw a script A sub n sine n omega 1 t plus phi n. So this is one of the terms from this Fourier series. And from equation 637, so I know that you guys all remember which equation that is, but just for myself, I'll remind us that formula, that equation, tells us that for a sinusoidal input, we get a sinusoidal to a linear system. We get a sinusoidal output with the frequency response function magnitude scaling the amplitude of the input sinusoid, and the phase of the frequency response function adding with the phase of the original input sinusoid. So we can say that this term, un, contributes to the output a term yn of t, which equals script a n times the magnitude of the frequency response function, and specifically not at any frequency, but at the frequency n omega 1. So this is the frequency of the input sinusoid, right? N omega 1. So the magnitude of that frequency response function at that frequency times the sine of n omega 1 t, so same frequency, so the output has the same frequency as the input, plus the original input phase, phi n, plus the phase of the frequency response function evaluated at that frequency. So this is just equation 637 from a couple lectures ago, but written specifically for this as our input, right? So each term in the Fourier series contributes this output. So each term in the input here contributes this output. Now, we can use the principle of superposition, right? Principle of superposition says if you add up a bunch of inputs, which you already knew the outputs for, you can find the output to the sum of inputs by just summing the outputs, right? So we found the output for each of these terms. If we add them up, we're going to get our output from the entire periodic input. So, applying the principle of superposition, the forced response of the system to periodic input u, so u being this whole thing, is y of t equals a naught over 2 h of j 0. So we'll come back to this term. But the rest of it is a sum over, so it's essentially a sum overyn's, right? So we could just write sum of yn, but we expanded it out and wrote this whole thing in there. So we sum up each term, and that gives us our output. So before I talk about this DC offset, this is cool, right? So this is a big part of why we introduced the Fourier series. That also gave us access to thinking in the frequency domain, right? But the Fourier series allows us to write any periodic waveform as a sum of sinusoids. And the principle of superposition allows us to construct solutions, construct responses, construct outputs from a sum of input responses. And that's what we've just done. So now we know, so this equation 646 is actually the solution for the forced response for any periodic input. If you write a Fourier series of the input, you have the solution for the periodic input, what the forced response is. So it's really nice. Like, it's just, you have your solution right away. And it's very intuitive as well. It's like, oh, we know that if you put in a sinusoid at this frequency, we scale the amplitude, we shift the phase by the sort of Bode plot, by the frequency response function, right? You just do that for a bunch of terms and sum them up. It's pretty cool. So you can do this also, so we'd use this trigonometric form because I think that's usually the most intuitive for people. But you can also do this for the complex Fourier series representation with each input component being Cn e to the j n omega 1t. So that's the Fourier series representation in the so-called complex form. And then 648 is the output given this input. So you go through the system and you get this output for that term. And you get the principle of superposition giving you this whole sum here. Oh, I didn't talk about this DC offset term. This term might freak you out at first because it's h of j 0. So that's frequency equals 0. And sometimes frequency equals 0 is a scary concept, but it's not. No need to be concerned. That is just the frequency response function evaluated at omega equals 0. So if that's equal to 1, then this term goes away, but it might be equal to 5 or 10. It's the so-called DC gain of the transfer function, okay, or the frequency response function. All right, so we've got the two forms of it. So 649 and 646 tell us that for a periodic input, we obtain a periodic output with each harmonic omega n amplitude scaled by h of j omega n, magnitude of h of j omega n, and phase offset by the angle of h of j omega n. As a result, the response will usually undergo significant distortion called phase distortion. Okay? The system H can be considered to filter the input by amplifying and suppressing different harmonics. So you're putting this input with all of these different harmonics, with different amplitudes and different phases in, and the system, for a given frequency is going to amplify or decrease the amplitude of the component at that frequency, that harmonic. So when it comes out, it's going to be distorted, right? It'll be a copy of itself if the system doesn't do much to it. It'll just be a copy of itself maybe that's scaled, but most of the time you're only going to scale certain frequencies and you're going to change certain phases, and then what comes out can be a garbled mess compared to what went in. So this is especially of interest to us when we were talking about measurement systems. So those who took my instrumentation class, we talked about this. But if you're trying to measure a periodic waveform, and every measurement system is a dynamic system, has a transfer function. So if you're trying to measure some periodic waveform and you have phase distortion in your measurement instrument, which you will, you have to be aware of that when you reconstruct what the measurement is. Okay, so it's an important concept. But not just for that. So if we think about this as filtering, so we don't have probably a ton of intuition on filters yet, but we do know that audio filtering is something that happens, and we know that that's a pretty common thing that we'll do. So say you have an old recording and it's got really high frequency, sort of like grainy noise stuff, like kind of background hiss to it. That hopefully happens at certain frequencies primarily, and not totally broadband. Sometimes it's totally broadband and you can't get rid of it by filtering only. But say it's pretty, there's like some region, like maybe high frequency noise that's coming through. What you can do oftentimes is you can run it through a filter that filters out that high frequency stuff, okay? And so that's typically maybe our first intuition into filtering, right? And how you would do that is you put it through a a frequency response function. So let's look at this Bode plot here. We'll talk more about it in a minute. That at high frequencies has a small magnitude. That means that whenever you have a component that comes in at a high frequency, it gets multiplied by a small number. And so on the output, that component's a lot smaller, right? So way out here at like, I don't know, 10,000 hertz or 100,000 hertz or a million hertz, whatever, if you have a frequency component in your input signal and it multiplies 0.000001, which might be the magnitude of your frequency response function out there, then in the output, that component's going to be really small. Okay? So that's like the sort of first concept of filtering and signal conditioning. But this is true not just for an electronic signal, okay? So it's really important for electronic signals. We care about that when we're doing measurement, especially. But it happens for any system. So I've used this before, and I feel like this one has some intuition for you guys. I try to connect with things that are like somehow physically you guys have done. You guys have pushed people on a swing before, right? Okay. So, I mean, I don't know. Something that people used to do. I don't know what kids do these days. But anyways, you push somebody on a swing. Whippets, yeah. You're pushing somebody on a swing, and at low frequency, when you push them, like super low frequency, so we're down here in this region, super low frequency, whatever the amplitude is that you push them, they're just going to essentially follow you, right? It's like 1-to-1. Like, if you just go super slowly, they're just going to swing slowly with you and think you're creepy, right? and then if you start to speed up a little bit and you reach that frequency that the swing wants to swing at, right? So if you start, it's like every like 1 or 2 seconds, boom, boom, right? And then like their amplitude increases, right? And you see this growth. This is actually sort of a second order system response where there's a little bit of a resonance there. That's the natural frequency of the system. If we push at that frequency, we actually see the amplitude of the oscillation increase. But
is this due to like constructive interference?
It's due to the natural frequency of the system. So the system wants to oscillate at that frequency. If you were to like offset it from 0, like you were to like pull a person like up and then just like let them go, that's about the frequency that they would swing at. If you push at that frequency, you're going to add energy at sort of in the right at the right frequency for the system to gain energy. But if you then you start pushing really fast like this, that's like if you do this,
They're still gonna think you're creepy.
they're gonna think you're creepy again. But also they're not gonna even move with you, right? If you go too fast, like they don't even move. Like if you like push pull like this, it's like they just sit there, right? If you shake them now, but if you go too fast, okay. If you go too fast, then they don't respond much at all to your. And if you go super fast, it's just like it's like you're like have like a cell phone vibrating on them, like zzz, like they don't move. The swing doesn't move, right? It's going to the frequency is too high to have any effect. That's kind of what's happening. Even a mechanical system can act like a filter. It responds to certain frequencies, and it doesn't respond to other frequencies, okay? And so this thinking about a system in terms of as a filter of frequencies is really common. And when you get to vibrations, that next class, then in your senior year, it's thinking like that, like all these, especially mechanical systems, as being, often we'll even call them filters for input periodic signals. Okay? So, let's see. Did I cover all of that? Yeah, so this way of thinking is very useful for the study of vibrations, acoustics, measurement, and electronics. So it's like a whole bunch of stuff. And even just your design, like, so you guys have all seen like videos of like galloping Gertie and all that stuff. Like, it's commonly explained as being a resonance phenomenon that happens. So these sorts of things are important when you design all kinds of stuff, not just if you're like a vibrations expert or something. Like it comes up in a lot of applications. Okay, all this can be visualized via a Bode plot, which is a significant aspect of the Bode plot's analytic power. An example of such a visualization is illustrated in figure 6.9. So let's take a look at this figure in detail. So, you have some input that has a spectrum, right? It's a Fourier series. Remember how when we broke a signal down into a Fourier series representation, you could plot its line spectrum, right? So 6.45, this representation of our input, might look like this if we did its line spectrum. So this is our script A, and input magnitude. So for different frequencies, oh, and there is one thing with this figure. I'm working with somebody to bring in some of his material, so I apologize. Oh, this is a little thin on there, isn't it? There. I apologize for the notational difference here. These omega zeros, we use omega 1 for the fundamental frequency, but in this notation, it's omega 0. It's another common notation for the fundamental frequency, but slight difference in this graph. So the ANs, the script ANs, for each value of omega, for each frequency, for each multiple of the fundamental, we have some amplitude, right? We also have some phase. So this could be like plus 90, minus 90, something like that, probably, something like that. These are the amplitudes. So there's our periodic input. In the time domain, it's hard to visualize what that would look like. Like, it's some periodic signal, but it might have some weird, like, funky pattern to it, but it'll be periodic for sure. So this is at least the beginning of its line spectrum. These can go off to infinity, right? So there could be components all the way down. But yeah, so we've got this magnitude and phase of the input. Then we put this input signal into our system with our frequency response function h. Okay, the frequency response function h has a Bode plot like this. And actually, this Bode plot is slightly atypical in that it is not in dB. It's just an amplitude. And the reason we're doing that is that we're going to think about multiplying instead of adding in this example. Because remember, when you have a Bode plot in dB and you multiply two things together, you in fact just add them because it's logarithmic. But if you do it in magnitude and not in dB, which is what this one is, you can multiply by it instead, which is what we want to do. What we're doing is we're going to say, okay, at the fundamental frequency, we have an AN of whatever this is. So A0. We multiply that by, let's follow this frequency down. We multiply that by this magnitude. Okay, so this is magnitude of, so h of j and then omega naught, right? So at the fundamental frequency. Multiply it by that, and it gives you, continue to follow it down, it gives you the output magnitude, this value, which is A, this value, which is A n times, so S, not A n, A0 times H, the magnitude of H of J omega 0. Right? And if we were to do the fifth one, it would be A5 times the magnitude of H of J omega 5. Right? So the input has a spectrum. The Bode plot filters it, right? So if we're thinking just magnitude for now, anything in this region, say this is 1, which it often is. Say this is 1. Anything in this region, you multiply by about 1. Okay? Yeah?
Would it be omega 1 versus omega?
Yeah, so that's, I apologize for that. This figure that I'm using from a collaborator of mine who's given me permission to use it, he uses omega 0 as fundamental frequency. We used omega 1 as fundamental frequency. It's a little notational difference, and it's a little confusing. So
I'm just trying to see, because for us, omega 0 would be the one on the very left.
yeah, that's right. That's right. It is. I agree. That's super confusing. 0 is the new 1. I don't know. What do you think?
I'll take that.
He's pretty happy with whatever, it seems. Okay, so notice that, so down at these low frequencies, we don't expect this amplitude to change much, right? Because it's going to be multiplied by 1. So this input amplitude is pretty close to what the output amplitude is. At this resonance, so this is a resonance here, we have the output greater than the input. And in this region, we expect the output to be larger, so like maybe a factor of 2 larger than the input. So that happens at about 3 omega naught, right? So if we follow that down, we expect this one to grow, right? So we keep following it down, and it was down here before, so it's like twice the height, right? So that's good. But then we see that our Bode plot magnitude tapers off. So at higher frequencies, we're expecting the input to get diminished, right? These are going to get filtered out, we would say, or reduced in amplitude. So we expect these guys to end up being quite small. And they do. They get quite small. So that's the sort of why the Bode plot's so powerful, is that we can think of a periodic input with different harmonics in it at different frequencies as being filtered through the magnitude spectrum, magnitude Bode plot. And then the phases, of course, shifted. So in this Bode plot, we've got, say, it's probably a second order system, so it goes from like 0 to negative 180 degrees. So we're going to take these guys that were, plus and minus, say, 90 probably, and they're going to get shifted down progressively. So starts off without much shift because we're adding 0 phase down there. And then as you increase, they get shifted down by this amount. Okay? Okay. What do you guys think? I think it's pretty cool. I like it. Papa Francis likes it. Yeah.
Why is it that with where your initial A naught is,
Yeah.
the frequency the magnitude is the highest point there?
Why is it the highest one?
Yeah, why is it that the highest point versus your 3 naught?
So the input spectrum can actually be anything. So I picked this sort of arbitrarily, right? So this A naught didn't have to be the highest one. 8 omega naught on the input could have been this high.
I'm just trying to see the relationship between that magnitude and the Bode plot down there, because you have the peak on the Bode plot at 3 omega naught.
Right. And so these are independent of each other, but when they get combined, then the bottom two graphs are showing what the combination is.
Okay, so the system magnitude plot for the Bode plot is not dependent upon the input magnitude.
Exactly.
That's this one.
Okay, gotcha.
So the input is whatever it is. So you could put into a system whatever kind of weird periodic signal you want. But and then the Bode plot is going to be whatever it is, because that's modeling the system, right? Like we would draw our linear graph, maybe we would use impedance methods to find what the transfer function is for the system. And that's independent of the input. So H is independent of what the input is, the input's independent of what H is. Then when you combine them together, when you put that input into the system, how the system affects that input is what the Bode plot's describing for you. And what this output is showing is the scaling of these magnitudes of the input. Scaling of the magnitudes of the input by the magnitude of the frequency response function. And then the shifting of the phases of the input by the phases of the frequency response function. Yeah. Okay. So I will say, the next couple homeworks I think are going to deepen your understanding of the frequency domain. And the final exam is cumulative. So, yay. Yeah, yay. But of course, the material toward the end of the course will be more focused on, because we did have a midterm over a lot of the stuff. So the focus will be on the material we cover from, today to the end. But there will still be, so like this frequency response stuff is still going to be a part of the final exam. So don't dismiss these next two homeworks as being irrelevant, because we're moving on to controls now. It's still really important stuff. Yeah.
Well, when officially are we going to be on that lecture for controls? Is that next week or?
11:41 a.m. today.
Oh.
We're going to do it. We're going to do it. Yeah.
How about the homework for this week?
Sorry?
How about the homework for this week?
How about it?
Yeah.
I don't know. What do you mean?
I mean, we posted like chapter 8, but we didn't do it. So are we doing it again? Or
So the homework is, let's just go here. The homework is, it's assignment 9. So this is the one that was due last week, before the exam. And then so this week we have assignment 9 and a quiz over it on Friday. And then next week we have assignment 10, both from chapter 15 of the system dynamics. I shortened my lecture notes and I didn't go into an 8th chapter in the dynamic systems, because I essentially covered all the material that was needed to do that, and I wanted to leave a little bit of room to discuss some other things at the end. So you have all the tools you need to answer the homework problems. There's one that is not completely discussed, but it's not until next week's homework. And so I can help you guys with that. When you guys encounter one where you're like, I don't know how to solve this. Okay, when you encounter one that nobody knows how to solve in the class, then come talk to me. It's next week. It's I think it's 1517 or something. And you have to take an inverse Laplace transform, I think. You'll be fine. We talked about them. We talked about the tables. You guys took it in your class. It's not like you have no idea how to do this stuff. But okay, cool.